Okay, my great pleasure to introduce today's speaker, Riccardo Rattazzi, who is an old friend and one of my favorite physicists. And he'll be visiting us for 9 months, so this talk is partially an invitation for everybody to talk to Riccardo. Riccardo is very well known for working on all kinds of things simultaneously, starting from fluids to cosmology. But for this colloquium, I asked him to talk about something which is really close to his heart, which is particle physics and character problems. So that's what we'll hear from Riccardo. Well, I should say Riccardo, he graduated from Pisa in 1987. I think he's one of these last Italian physicists who actually don't have proper PhD. So we should have, with grain of salt, whatever he'll tell us. But
don't take me too seriously.
Then he spent some time at Berkeley, Rutgers, and CERN, and again at CERN, and was at Lausanne, Lausanne for the last 16 years, and now he's here. So, go ahead.
Thank you very much, Sergey. So, first of all, I hope I will manage in 1 hour. I'll do my best. What I will present today is a theorist perspective on modern contemporary particle physics. I will tell you one story, which is based on one point of view, and as it's often the case, it's clear that the story can be enriched and modified by taking different points of view, and maybe in the discussion, other points of view emerge. Okay. So this talk is divided into 3 parts. In the first, I will review the main concepts at the basis of particle physics, and in fact also physics, some of them in general. And then I will then just perform a sort of critique of the structure of the standard model, and then present the attempts, some attempts, or the main attempts to go beyond, and the paradox they raise. Okay? So let me start with the basic concepts. Okay, so this is a colloquium, so I intended it as very basics. Okay, so the principles. So particle physics is that sector of physics where both principles of modern physics, that is quantum mechanics and relativity, okay, and relativity, well, I don't need to say much about quantum mechanics. Let me just elaborate on relativity. Relativity concerns the invariance of the laws of physics with respect to a certain class of symmetries. These are space-time symmetries consisting in space-time translations, translation in time and space, rotation, and boosts. Now, these symmetries were already at the basis of.
Well, we can hear somebody in the talking. So Sergey needs to do something, so we can only hear you.
Do you know what
I already have one colloquium that was Zoom on.
Oh. All right. You keep talking and I'll see what I can do here.
Okay. So relativity, the invariance under this set of symmetries, in fact, was already postulated at the beginning of modern physics by Galilei. The Einsteinian relativity is just a deformation of the invariances postulated by Galilei and at the basis of Newtonian physics. And the difference is neatly represented by considering the commutation relation among the infinitesimal generators, which, by the way, do I have a pointer? Or a stick would be perfect. Okay, I can go like this. So in the case of Galilei, sorry guys, I should have thought about this earlier.
Sorry about that, but there was a stick at this moment. 10 years ago, there was a stick.
I cannot see. Do you see that one?
No.
But Eliezer had a nice pointer in the morning. Maybe he brought it with him.
Maybe he stole it. Sorry, I cannot see anything. Am I doing it wrong?
No.
Oh no, it's here. It's here.
Okay.
It's here. Okay. So the main difference is in the fact that in the case of Galilei, boosts commute, and in the case of Lorentz or Einstein, they don't. And it is this apparently minor difference, well, it's not minor, that leads to the fact that in Einstein relativity there exists a limiting speed interpreted at the speed of light. That's essentially, so this is just what implies the existence of limiting speed. In a sense, the relation between Galilei and Lorentz is the same that exists about the Euclidean symmetries on the plane and the symmetries of the sphere. So it's a deformation of the symmetry. Anyway, this is the symmetry that works. This Einstein symmetry, Lorentz imbalance. Now, the consequences of, in a nutshell, the consequences of putting together quantum mechanics relativity. The first thing, as I said, the existence of a limited speed. That implies that instantaneous interaction between objects that are distant is impossible. And for entities to interact when they're far away, you need a medium, you need an agent. With this agent, we call it a field that communicates the interaction. It's very much like imagining two fishermen on boats on a lake who decide not to talk to one another or to signal with light. They can, in principle, communicate just by jumping on the boat and communicate through waves that propagate on the field. The field is the surface, the height of the surface of the lake. This is classical. When you add quantum mechanics, there is more, okay? Well, according to quantum mechanics, the configuration space of a system is in one-to-one correspondence with the Hilbert space. And everything must be represented in the Hilbert space, in particular, the generators of the symmetry, okay? The symmetry algebra should be represented in the Hilbert space, and the Hilbert space should consist in sum of blocks, and each of them is a multiplet representing the symmetry, the algebra. And so, studying what you can have in the Hilbert space, what is the classification of what happens in the Hilbert space, corresponds to classifying the reducible representations of the Poincare algebra. And the reducible representations, you're familiar from angular momentum, are characterized by principal quantum numbers. So what are the principal quantum numbers? This is a mathematical problem, okay, of the Einstein relativity algebra, where there are two quantum numbers, m and s, with interpretation of mass and speed. So what are these building blocks? Well, these building blocks are nothing but particles, okay? So particles are, even if we had never seen particles, if you're a mathematician, an abstract mathematician living outside of space and time, given that algebra, it would deduce, knowing quantum mechanics, there must exist particles. In fact, the existence of particles can also be seen by considering fields and quantum mechanics. You know, fields classically have waves, and classical waves can have arbitrary height. It's a continuous parameter. But you know that quantum mechanically everything is sort of discrete. So because of quantum mechanics, there will always exist a wave for any field of minimal amplitude. What the hell is this wave? Well, it's nothing but a particle. Okay, so particle just arise as the minimal amplitude wave. So quantum field, this is how to see how the things are correct. So particles are not just accidents of physics, they just follow from principles. So when we do particle physics, not just collecting daisies, but it's just working with the entities that are unavoidable because of the two principles of physics, which is quantum mechanics and relativity. This is not to tell you that collecting daisies is bad, because we can talk about how Darwin understood a lot about evolution just by looking at the shape of flowers. So there's also interaction behind that. Okay. So causality in relativity is more interesting than in non-relativistic theories, and it becomes even more interesting when you add quantum mechanics. In order to implement a proper causal relativistic quantum mechanical theory, turns out that the particles with fields should follow a certain statistics, and what we know, this is a speed statistic theorem, again, follows from two principles. Quantum mechanics and relativity, integer speeds, particles are bosons, should satisfy Bose-Einstein statistics, by half integer speed should satisfy Fermi.
I see you talked about evolution, but then there was a species which did not evolve, which are the continuous, the infinite representations of massless particles.
Yes.
So maybe as you mentioned,
it
evolution,
would be- it
they
would be-
did not evolve.
They may be in some continent we have not yet landed on. The seventh continent, okay? Well, they exist. Do you want to add something more? No, it's okay. I would be happy to discuss these other funny representations that are representations with zero mass, okay? And which happen to be important in the sense, truly, they exist. At least we've seen them, we keep seeing them. Now, there are specific representation in the classification that I presented before. There is the possibility of having zero mass particles. And what it turns out is that the zero mass particles with spin are peculiar because even if they are spin, they come only with two polarization. You're familiar with the particle at rest with spin 1 has 3 polarization, with spin 2 it has 5. Well, in the case of massless particles, consistently you can have only 2, the maximal ones, either +2 or -2 or 1 and -2. The photon has a -1 polarization spin, okay? And the reason for that is related to the fact that the massless particle is restless. You can never bring it at rest. It always has a momentum. A massive particle, if you go fast enough, you'll get at the rest frame where the momentum is 0, and then if you do rotations, you will have to fill a representation of the SO3 algebra, which has 3 polarization for spin 1. Well, in the case of a massless particle, you can never bring it to the rest frame, and that's the reason why you have the you don't need to have all the polarizations, and so nature likes to do things in a minimal way, and this small or short multiplets do exist. And in fact, what is more interesting, even more interesting, is when if you want these particles to interact, okay, then the fact that they come in these short multiplets places powerful constraints on the structure of the interaction. You could say that, they're subject to geometric constraints that take the form of what we call gauge symmetry. In other words, the interaction of these particles in short multiplets are very, very constrained, and in a sense, geometrical. So for instance, the standard model, they are described by the SU3 cross SU2 cross U1 B group. And in fact, gravity itself can be viewed as a gauge symmetry theory based where the symmetry is the general coordinate transformation. This is basically all I have to say about the principle. So you see, this is just putting together quantum mechanics and relativity. Then all this set of these principles and the following and their consequences are put together in a mathematical, are encapsulated in a mathematical construction known as quantum field theory. Okay. Quantum field theory, as far as we understand, is the most fundamental description of nature we possess. Okay. So what is a quantum field theory? How do we build a quantum field theory? Well, quantum field theory consists in a choice of fields, okay, very being superficial, but I'm not saying anything drastically wrong. The choice of fields that are put together according to the principles of quantum mechanics and relativity, and they're put together into an action or a Lagrangian that describes their dynamics. If you want, the fields are the actors, and the Lagrangian is the script. Okay, and as I said before, there is essentially a one-to-one correlation between the fields and the particles associated to their smallest amplitude waves. So you can see the fields are in one-to-one correspondence with particles. So, okay, and the next step is to measure physical quantities. Now, in particle physics experiment, to the very driest, describing particle physics in the driest possible way, that we are measuring scattering amplitudes between particles, okay, and the computation of the scattering amplitudes is just corresponds to the computation of the correlators among the corresponding fields, okay, using the domain. So you have the principles, you have the fields, and you put them together in a Lagrangian, and that predicts the physics, quantum mechanics, and relativity. Now, standard model is just a particular incarnation of quantum field theory. One particular incarnation where the gauge fields are associated to these groups, okay, to this group, this product, SU3, SU2 cross U1, and diffs, if you also want to consider gravity, and in a sense, why not, although I will not talk much about gravity today. And then there are other fields that whose existence we were able to establish by experiment. One is the Higgs field, is a bosonic field, and here I indicate the quantum numbers of these fields. These fields will have to transform in specific representations, in representations of the gauge group, and the gauge group is SU3, SU2 cross U1, so the Higgs scalar doublet is a singlet of SU3 and a doublet of SU2, and well, okay, there's charge 1 under it. And then there are a set of spinorial fields whose corresponding particles have spin 1/2, which come in specific, bizarre, if you want, representations of the gauge algebra. Okay, they also have some they have specific charges under this U1, which is associated in the end to electric charge. And in a sense, we understand these quantum numbers in a deeper way, even they seem bizarre. But what we don't understand is that this structure, this set of fields and the corresponding particles in nature and in the standard model exist repeated 3 times. In other words, this structure comes into 3 families, which are 3 replicas that from the point of view of these quantum numbers are the same, but they differ for other interactions, okay? So we don't understand the origin of these 3 families. Although we have measured that there's a whole field of physics that measures the properties of this family. Now, Q of t, whose secrets or principle we deduced by observing this unique reality where we happen to be born, which is things here, the experiment into here, actually makes us builder of possible worlds. Once we have deduced these principles, we could imagine quantum field theories with different gauge groups, with different particle content, and there is a huge variety that we can think of. Okay? We can imagine different worlds. We can imagine worlds where there are 3 different types of nuclear forces, not just one. Here, the nuclear force of our world is the one associated with this SU3. We could imagine a nuclear force associated with SU4 or SU7, SU15. There is a big world of possibilities. So it makes us build a possible world, but it offers an infinity of them, while we have only one. So the question, I mean, you're immediately confronted with the question, how was the world we live in, the structure of the standard model, picked among such infinity? Who ordered that? I don't know. But you see, but the I cannot say. I mean, we have got to the point where we can ask this question today, and I think that's already interesting. Now, what I would like now to do, in principle, is to go and describe to you in a critical way the structure of the standard model. Okay. However, in order to do that, which I just presented here very briefly, just at least the field content. However, in order to tell you my story, I need to recall you some basic facts of physics, okay? Really basic facts, okay? And which is what I'm going to do for the next few transparencies. 8, maybe 8 or 9. So let me start, okay? First question, why can we do physics, okay? This seems like a ludicrous question, okay? So let me specify what is physics? Well, physics, in a sense, okay, or to a large extent, is being able to make infinitely many predictions starting with a finite number of inputs. Okay? And the question is, why is this possible? Why don't we always need an infinite number of inputs? If you want, it could be a logical possibility. In that world, it would be hard to make any statement. So, to in a sense answer this question, I would just answer this question with a simple example. And the simple example is just from electrostatic is the multiple expansion. So consider a small distribution of charge, a small bundle of charge with size r micro, and assume that we are in a static situation. I'm not assuming anything is moving, and I'm observing the electrostatic field at a distance r that is much, much bigger than the size of the object. And we have learned in electrostatics that in this situation, it's convenient to express the electrostatic field, or the potential of the field far away in a multiple expansion, which is an expansion in inverse power of r. And generically, at each further order in this multiple expansion, you get contributions that are suppressed with respect to the leading one by the ratio r micro over r to the n. Okay? So that's the multiple expansion. So now, what is the story about the multiple expansion? Well, if you're working, which is always the case in any situation, at fixed accuracy, and you're going at large r, okay, if your accuracy is fixed, then you can measure only a finite number of terms in this expansion. And what you're measuring are the multiples, the monopole, the dipole, the quadrupole, and so on. So given your accuracy, you can measure only a bunch of them, okay? That's certainly a limitation, but it's also a bonus, because now within the same accuracy, imagine you have measured all your multiples up to the quadrupole, let's say, given your accuracy, by making measurements around the North Pole, in the region around your distribution far away. Then with those inputs, you can extrapolate the field away to the South Pole and elsewhere. In other words, you can use it to predict the field in points where you have not yet made measurements.
If it works, of course.
If it works, of course. You could have magnetic field equal to 100 Gauss at the South Pole, for all we know.
Yeah, okay.
Until
you're talking about the South Pole in that sense. Yeah, I'm talking about, yeah, I'm you know what you are.
Maybe I misunderstood you. You said that by measuring multiples, we can predict the field everywhere.
With some assumptions, okay?
Right, by measuring multiples everywhere, we can predict the fields everywhere, which is tautology, but okay.
Okay. I mean, there's always some assumption about, you're saying that there is perhaps a, you're saying if there is
Until I go to the South Pole, however accurately I measure the field in New York, I know nothing.
Well, I mean, when I extrapolate, I always have to make some assumptions, right? Right. Okay. Yeah. Fine. Okay. Then, when I go there and I measure, I can check my assumption. Okay. In that case, I have a finite number of inputs, and then can predict it everywhere. I really don't see it. Anyway, we can debate that. Okay. Now, and
It's all philosophical anyway, so it makes no sense until you do it.
Okay, fine. So this property, which shows that, I mean, that when you go to long distances, you only measure you're only sensitive to a finite number of parameters, is what implies that different objects here can look the same at your level of accuracy, is what we call universality. Okay, there are different objects and they look the same. And the converse, when you go to smaller distances, work and fixed accuracy, you get more and more multiples are needed. And at the point where you get to distances of order the size of the object, you virtually get infinitely many of them. Now, what can happen in that case is that you may discover that your distribution is given by some simple configuration, and then you go on. But in principle, at this stage, you have infinitely many parameters needed. Anyway, all I want to say with this example is that the ability to work with a finite number of parameters is related to the existence of separation of scales. Okay? And that is the case, it's the case in all other situations. Think about the atomic model, okay, you can predict, you can study the properties of the hydrogen atom without worrying about the fine properties of this much smaller physics scale happening at the level of the nucleus, or in planetary physics, in celestial mechanics, the fact that the planets are big, but still they're much smaller than the distance separating them, allows us in first approximation to treat them as point, and then we can systematically refine, very much like in the multiple expansion. Similarly with fluids, long time scales that are much longer than the interaction time among particles, we can get a simplified description with fewer parameters. But as we move to timescales that are shorter and shorter, we need to add more terms. That's That's the story about all of physics. And there is one crucial aspect about the existence of, so separation of scales is the essence of, it's very much intrinsic in our ability to do physics. Another aspect which is related to the existence of separation of scales is that, which is related to the fact that we get a finite number of parameters, is that no matter how complicated our system is, the description becomes simpler. There's a simplification. And the simplification is often associated with the occurrence of symmetries, we call accidental symmetries. And this I can illustrate with the example of the spherical cow. Okay, so take a cow. Okay, you're close to the cow. You look at it. It has horns. It has a tail, and certainly it's not the same if you rotate it. It's not rotational invariant. On the other hand, if you kick the cow and you send it far away, it will look like a point, and the point looks the same from all the direction you look at it. So you have apparently an SO3 symmetry, while even if the object does not have it. Call a symmetry that arises because there's a big, because of that, an accidental symmetry. Now, this is a cartoon, but you can be slightly more technical when you consider, again, the example of the multiple expansion. Again, you expand as shown before, and now, as you know, the monopole, which is the leading term at very large distances, is a scalar, the dipole is a vector, the quadrupole is a two-index symmetric tensor, traceless symmetric tensor, and so on. And then there is indeed a hierarchy of symmetry associated with this object. The leading one has the full rotational symmetry. That's if you want the spherical cow. The next correction, the cow actually has a head and a tail, so it's a dipole. And basically, when you go to the quadrupole, you break all the symmetry. Of course, you could imagine a quadrupole that is aligned with the dipole in some way, so that you have still some U1, but generically it's like. So the further you go in the expansion of the multiple, the less symmetry you have. Now, so that's essentially the story, okay? So the possibility of working at distances that are much larger than the fundamental length scale of your system, which could be in length or time, allows us to have simplified descriptions. And not only that, but we can make our description systematic when we expand in powers, what we call a derivative expansion in powers of this ratio. And at finite precision, we only work with a finite number of parameters, and we have two things that emerge in that, is the simplicity and also accidental symmetries. And now I want to take a little parenthesis or in another parenthesis, and I want to say something about symmetry, which is truly basic, but which is important. Now, okay, in this perspective, symmetries do not need to be fundamental. They arise just accidental, just as a result of the existence of separation scales. And now, as we know, symmetries are nice and useful when they're exact, but they're also perhaps even more useful when they're not exact. And that is through the notion of selection rules, okay? So they still allow us to analyze how physics work, even when they're broken. And the trick is simple, okay? And let me give you an example. Take for instance, an atom, okay? And in its ground state, normally you think the atom is, you can think essentially what the atom ground state is in a spherically symmetric configuration. In this ground state, therefore there will be no dipole polarization. Now imagine you put the atom in an electric field. Okay, now you treat the electric field as a parameter. Okay, no, it's a field, but at the level of atomic physics, you just treat it as an external parameter. And we pick a direction, it breaks rotation. So what happens in this case? Well, you no longer have rotation to work with, but you can formally reinstate rotations by formally assigning transformation property, the obvious transformation property to the vector field, to the electric field, maybe transforming as a vector. Once that is the case, you formally recover your symmetry, and all your expression now have to be covariant under the symmetry. So if you want to know what the polarization of the atom is, well, this is a vector. On the right-hand side, you must have another vector, and this is the general form. Of course, using this argument, you cannot tell whether it will align or anti-align, but you can still say something, okay? Of course, you would think, oh, but that's obvious because it stretches this way. But think, for instance, what would happen in 2 dimensions, you have parity violation. In that case, you have another invariant, which is the Levi-Civita to index tensor. In that case, you can also have a polarization in the orthogonal direction. So things can be less intuitive. Now, we are familiar with the fact that, that selection rules are normally associated with slightly more advanced subject than basic physics, because we learned them in quantum mechanics, already not in the very first days of physics when we studied, but actually even good all-dimensional analysis is a form of selection rule. And in that case, well, in the case of rotations here, the symmetry associated corresponds to rotating the reference frame. In the case of dimensional analysis, the corresponding symmetry is associated to the change of the units of measure. Okay? The change in units of measure acts, for instance, on coordinate. If you change the unit of coordinate or unit of time in the following way. Now, this is normally not a symmetry, but because there exist parameters that do not respect these invariants. But again, if you allow those parameters to form and transform very much like the electric field in the case I described before, then you can form a Rayleigh state in the symmetry, and then your equations will be covariant under this. So take the example of the pendulum, okay, well, we know very well, right, that this is the result. And it's the form of selection rule. This was known, I think already Euclid, I studied before giving this talk, had the notion of dimensions. Newton as well, but it took a French to formalize it, like the way we do it now.
Who is this? We don't know.
Eh?
Who is the gentleman?
Fourier. Yeah, I wanted to just say that this was known to Euclid, Newton, Galilei, sort of. Before I had Galilei here, and I was saying this story that I heard that Galilei was in the church and he was looking at the ticking of the clock. He had measured G, and then he deduced that the dimensionality worked. That never happened. So then I changed my story.
But he did elephants with their bones.
He did elephants, the bones and the things. Yeah, he thought about scaling laws. But all this was formalized. It took a French to formalize all this. You need a French mathematician. Okay, so I'm saying all these basic things because they will intervene when I will talk about the structure of the standard model. And it's also in a sense to react to the critique you hear sometimes when the reason I will show in a moment are normally present, oh, but this doesn't make sense of normalization. I just want to say that the things that we present are just as basic as this. This is the reason why I'm emphasizing this. Okay, so now let's close again. Let's close both the parentheses and both the brackets, and let's get back to quantum field theory. Now, in quantum field theory, you have relativity and quantum mechanics. So relativity, the microscopic length and the macroscopic time can be treated as the same thing, okay, through the speed of light. Because of quantum mechanics, time is 1 over energy, and 1 over energy is 1 over mass because of relativity. So in a sense, in quantum field theory, we can think of the microscopic length or time scale can be treated as the inverse of some mass scale, okay, the inverse of some energy, okay, and very much like in the multiple expansion or in everything else in celestial mechanics, where expanding the dynamics in powers of the microphysics scale are over the macroscopic length scale. Similarly, we should expect that quantum field theory follows the same rules, that whatever we do will be an expansion in 1 over n. Now, this thing that seems obvious, saying that quantum field theory is not different than anything else we do in physics, surprisingly took time to become the way of thinking of particle physics. It only was became so in the 70s with the work of Wilson and the work of Weinberg on effective field theories. And I must say that there are pockets of people that still resist this perspective somewhere. I don't say where, but in various places. And one reason why people were not thinking this way is because the technical complications that came with treating infinities and normalization in quantum field theory was in a sense clouding the obvious. It was putting like a sort of cloud on this very basic fact. And let me tell you how this works, okay? So let me discuss how we should see now quantum field theory or effective quantum field theory. Let me consider the simplest possible theory of a scalar field, okay? So the idea is that once you say what field you have in the symmetry, which is relativity symmetry, then you can write everything, okay? You can write any term. And the first term you can write down is the gradient term, okay? And now, by simple dimensional analysis, the Lagrangian has dimension energy to the fourth, because it should give you an action when integrated over space-time. So given that the derivative at dimension 1 over length, which is energy, then the field has dimension energy. Therefore, the more power of fields and the more derivatives you have, the higher dimension the object you have, and therefore the coefficient to fix the dimensionality of the Lagrangian should have inverse power of some mass. So that's the expansion. And this mass, we don't know what it is, but we know that, again, in the assumption that there exists a fundamental microphysics scale, is what will count. We'll measure the coefficients of this operator. Now, in a generic situation, it's like at midnight, every cow is black, okay? We don't see anything. If you don't have a separation of scales, very much like I said before, we have infinitely many parameters here. So in order to give a meaning to this construction, we need a separation of scale, okay? And what is the separation of scale that we can, the only meaningful separation of scale we can think here is the one between the mass associated with this particle, okay, and the fundamental microphysics scale, okay? And when that is the case, there is a range of energies there's a range of energies where you can treat physics in precisely in a calculable way. And let me explain, okay? So in this situation, what it turns out is that very much like in the multiple expansion, there is a finite set, okay? In the case of the multiple, it's just one. Very far away, you just have the monopole. But here you have three, and these are those that dominate when you are at energies in this range, okay? Let me explain that. So for instance, as I said, what we compute is scattering, okay? And let's compute, for instance, the 2-to-2 scattering. Then all you do with Feynman diagrams, okay, you can associate to each vertex some dependence on energy. You have the coefficients, and that's understandable. A scattering amplitude 2-to-2 is dimensionless. So if here you have 1 over m squared, you have put an e to get a dimensionless object. So therefore, the terms coming from this guy here will go like e squared, and if you're at energy much less than m, you can. It's thinkable that this is negative.
Sorry, can you explain why you divide phi to the 6 by m big squared and not m small squared?
As I said, I'm assuming that there is.
This is just an assumption.
It's an assumption, yeah. I'm just assuming that there is a separation of scales. So capital M, I will tell you in a moment how this could arise. Capital M is the scale of microphysics, and M is the.
But at this point, this is just your assumption, period.
It's assumption, yes. Yes. But this, you need it. See, you need it.
Yeah, I've read some books. I'm just asking what are you saying, okay?
We don't need to read books. You really trust books? Anyway, let me go back to what, so now, in the situation, therefore, where you have this hypothesis of separation of scales, this amplitude is controlled by this quartic, but then So you can measure the quartic using this amplitude, but then you can measure, you can now compute 2 to 6, 2 to 4, 2 to 6, you can compute higher point amplitudes, and what you find that again, they have a different form, but they're all dominated by the quartic, okay? So in other words, once you do these measurements, once you have this one input, you can, at this limit, compute infinitely many outputs. And you can also systematically improve it, okay? If your precision is slightly better, you can measure this, then you can improve and have finite number, but you still have a finite number of coupling.
And here, so this M2 is M square, right, in that expression that.
Oh, sorry, Massimo, yes, it's M square.
But
Yeah,
you are working at energies much larger than little m, just.
I'm working at little m, sorry, you're right, Massimo, should have put here bigger than m. It's just to say that, yeah. Oh, the reason is because I'm neglecting m in the amplitude, okay? But you don't need to be much bigger. That's true. So, precisely as I was saying, this assumption is necessary to obtain a simplified description. Okay. What can we say about this? Well, first of all, notice that this is because we have a scalar. If we had another particle, for instance, if you had a particle like a photon, then in the case of the photon, precisely because the photon has only 2 polarization, +1 and -1, there's absolutely no way to add a mass. Because if it had a mass, it would have a 3rd polarization. But degrees of freedom do not just come out of thin air. So if from the beginning you have only 2 states and your Hilbert space is constructed with only 2 states, +1 and -1, there will never be a mass. So this assumption of assuming a separation scale between the mass and the fundamental physics scale, in that case, would not be needed. And in the case of fermions, it's somewhere in the between, but it's similar to the case of the vector. The separation of scales can be argued in some way. In this case, it's harder, okay? And the most naive dimensional guess would be this, in which case we don't have any separation of scales, and that Lagrange is basically useless, okay? Because we are in a situation where we are, it's like in the multiple expansion, we are at distances of the order of the size of the object. Physics is described by infinitely many parameters. Now the question is, under what condition? That is naive guess, and I will say slightly more about how correct or not correct a guess like that is later on, but under what condition can we escape this naive guess, okay? As I said, in the case of particles with spin, there is a story, which I will not get into detail to tell you, because time is running short. But let me focus on the case of this scalar, because it's similar to what happens in the standard model. So what is a possible story of how this works? So a possible story is given by examples in condensed matter. I got this example by looking at a talk by Sachdev a few years ago. So, okay, condensed matter are nice models where we can think of how some microphysics at the level of material give rise to macroscopic quantum systems, okay? So an example is this antiferromagnet, okay? Which is essentially like a magnet, if you take the right variable, where it's a crystal, and you have, it's a solid, you have, you can, if you think that there is some, or there's a chance of having some macroscopic physics, you can describe the macroscopic physics in terms of degree of freedom, which is just the density of magnetization, okay? This is a vector, and you expect to have a Lagrangian. Particularly in that Lagrangian, there's a term without derivative, which we call the potential. Good. Now, generically, the mass, the quadratic term, and higher order terms in this situation are all controlled by the same scale, very, very much like we were discussing before. So there is no separation of scales. However, it happens that solids, or crystals, if you want solids, have the ability to exist in a certain range of a continuous parameter that is the pressure. In other words, you can take a solid, you put it inside a vise, and you start cranking, okay? If you crank too much, it breaks, but there is a range where it will still be a solid, okay? When that is the case, in that situation, the parameters that describe this macroscopic degree of freedom will be functions of the pressure, And it is thinkable that there are situations where at specific values of the pressure, one of these parameters, the mass, will cross zero, okay? If you're able to tune the pressure to that value, then you will have a situation that is the desired one I was saying before, where you have a separation of scale between the mass or the gap of your macroscopic mode and the fundamental scale that controls the expansion of the Lagrange. In that case, you have what we call universality. You have that physics at these lower energies that are allowed is described by few parameters. In other words, what we can say is that we can undo the natural expectation from atomic physics by tuning the pressure at a critical value in a landscape of options. So here the three critical things are tuning, critical, and landscape. The landscape is, well, it's a continuous landscape. It's the fact that pressure can take a continuum of values. Of course, what is the secret to achieve this is to have a good lab technician or a clever student who can tune the pressure at the right point. As far as I know, in particle physics, in our universe, we don't have this external lab technician. And that's where it's different. So with that, I come to discuss the standard model as an effective theory. Okay? Much?
7 minutes, 15 minutes.
15 minutes, okay. So the standard model, we should think of, you can think the standard model precisely as I said in the beginning. If you're given the fields, let's forget for an instant that this field's content, the content has been deduced from experiment. Let's say we're just a theorist playing with it, okay? We're given these fields, we say this is the field content, and now build a theory. So we go on and we write all the possible terms we can write down. And again, we start from this assumption that there exists some microscopic scale, M, which is the scale that controls the expansion of all the other terms, of all the infinite tower of terms, which is always there, okay? Like it's always there for any system in physics. The only way we can hope or think that these are less important is for some reason there exists a separation of scales, okay? If there exists a separation of scales, very much in the theory of the scale I described before, then we can, the first approximation describe physics at energy much below M, whatever M is, just by these terms. And so let's focus on the structure of these terms, okay? This is they are, okay? And here they are, okay? There are, this if you want, is what in the standard model is the analog of the monopole term, okay, if you want, in a sense. It's the meaningful object that exists that describes physics when there exists a separation of scales. It's the leading description of physics when there exists a separation of scales. Again, what would control the separation of scale? Well, again, there's essentially only one dimensionful parameter in this Lagrangian, which is the Higgs mass, okay? So again, to be able to make a separation between these few terms and all the big tower that comes, somehow there should be small or large separation of scales between this parameter and the others, okay? So what about, what can we say about this Lagrangian? So it involves 19 couplings, 18 of which we have measured. In fact, we have not just measured, we know their value, but we have tested in great detail of the dynamics, the peculiar dynamics they give rise, in particular, what we call here, these interactions are the Colloquium interaction that tie the Higgs and the fermions, and we explain the masses of fundamental fermions, not only the masses, but they are mixing between families. And there is a vast array of data that really tests this peculiar structure which is implied by this sort of interaction. The last parameter we measured is the Higgs mass, which we measured in 2012. Before that, in the Higgs sector, we only knew the ratio of the mass over the quartic, and that was known since 1932, essentially, when Fermi wrote the theory of weak interactions, the Fermi theory. And this is the coupling that controls strong interaction, weak interaction, and electromagnetic interaction. There's an important aspect of this Lagrange. So this is the more general Lagrangian of dimension less than 4, with operator of dimension less than 4, structure of dimension less than 4, that respects the SU3 cross SU2 cross U1 symmetry. We wrote everything. And so we wrote whatever could be written according to the gauge symmetry principle. Notice that the result of that, all the term will involve a fermion and an anti-fermion. That tells you that there is certainly in this Lagrangian a symmetry under which fermion and anti-fermion rotate with an opposite phase. Okay, so fermion number conservation. Something that you would not have if you have things like fermion-fermion, like in the Majorana term, okay, or an object with 4 fermions. Okay, and those we cannot write at this level. Okay, we cannot. Okay. And that has major consequences, okay, because it tells us that the number fermions, the fermion number is conserved. So for instance, something like where a proton decays into a positron. Proton is a fermion, a positron is an anti-fermion, and say a pion, pi 0, is not possible. Okay, so proton is stable. Or another thing is that neutrinos are massless. Okay, I will comment in a moment how good or bad that is. Okay, one last thing is that there is only one parameter out of this 19 which we have not measured, or if you want, over which we only have an upper bound, and that's the theta angle. And the presence of, and we really don't, the bound on this theta, which is 10 to minus 10, is so strong that we consider it a puzzle. And the possible solution to the puzzle is that we are missing certainly one particle, the axion. And that particle we are missing could also be the solution to another question, which I did not talk about here, and that is the origin of dark matter. Okay? So, but the crucial message here is that we have a vast and huge array of measurements that are all taken into account. So let me say it here. This Lagrangian beautifully explains all we see in the labs in the cosmos, except dark matter, but there is the connection I told you. In particular, it explains the peculiar structure, flavor, and CP violation observed in a multitude of very precise data. I will not even mention G-2 of the electron or electroweak precision test, which is quantum corrections in the electroweak theory. A consequence of the fact that I told you before, Fermi number conservation, is that baryon and lepton number are conserved, and they are, even if we didn't impose them. And so when a symmetry arises at the leading order in the multiple expansion, very much like in the monopole, we call this an accidental symmetry. So these two terms feature baryon number, which is the reason why we can get this talk. Okay? We are not exploding into a burst of positrons and pions. It's just an accidental consequence of truncating our Lagrangian to this order and assuming those are natural. Similarly, neutrinos at this level are massless. And this is actually very good, because even if we know the neutrinos have a mass, the mass is very small. So in first approximation, this is a big success. So neutrinos are massive, massively stable, and this is this. Now, the other part of the argument I'm making is what happens when you consider the other terms. Okay. Let's now consider this whole infinite swath of these operators that arise suppressed by whatever mass new physics scale you have there. Okay. As soon as we add this term, we found that effects that we do not observe become allowed, or effects that we do not observe or that we see as very small, like neutrino masses, are now allowed. Okay. Particular, this Lagrangian, whose structure I'm not describing here, I'm just telling you I'm just explaining, okay, I don't get into the details, allows a structure of flavor violation which is very different than the one we observed. Allows large electric dipole moments of particles, which we haven't ever observed, okay, fundamental particles like neutron, and they allow baryon and lepton number violation. Okay. So at this stage, the neutrinos acquire a mass, okay, and the proton can be unstable. So the very fact that these are like and this was never seen tells us that M must be very large. So, so it looks like if you have a separation of scales, we explain how large should it be? Okay, very quickly.
Sorry, do you need to go to dimension 5 operators to make neutrinos massive?
Yes, in the standard model, yes. Unless you add right-handed neutrinos.
Unless what?
You add right-handed neutrinos.
Right, or you
We don't
can
need-
choose to add
You can
right-handed
choose, you can
neutrinos.
choose,
Okay,
and
right.
at that point you have to explain why neutrinos are light.
And you have to explain non-normal.
I have to explain, well, no, I have to explain the separation of scale.
Right, right. Oh, okay, good.
Okay? By the way, even in that case, you have to explain the separation of scales.
Right.
Because you always need to explain the separation of scales. Okay? But right-handed neutrinos are not needed, okay, for any fundamental physics, unless you want to do other things, like, I don't know, explain baryogen.
But for example, some Shaposhnikov, he is
Sure.
doing it by right-handed.
Sure, he is happy to do that.
Okay.
I believe that.
All right.
Yes, you can add 3, 4, you could add 10 right-handed neutrinos. I add 0. If you add 0, the neutrino mass is immediately a higher multiple effect. Okay, and so then you understand, in a sense, that the fact that the neutrino mass comes from dimension 5 really makes a distinction between the masses of charged ferns who come from dimension 4 and these other guys that come from dimension 5, if you have a separation of scales. It's the same situation that you have when you have an antenna, okay, and you have wavelengths that are much bigger than the antenna. The absorption rate depends whether you have a dipole or a quadrupole. It's exactly the same situation. Okay? It's nice, okay, it's just sight. Of course, you have to explain the separation of scales. And I cannot. But once you have it, you understand these things very simply. In a sense, it would be nice to be able to use it. So anyway, back. I spent 3 minutes now. So back to the constraint. Well, the main constraint, the strongest constraint associated to proton decay, when you go to dimension 6, you can now write an operator which involves 4 fermions. They're all particles, not antiparticles, and now you're allowed to have this decay. Okay, we have experimental data from Kamiokande. They're observing a big tank of water for years, and there are lots of protons there, and they haven't seen any effect, and they can put this constraint. And this constraint can be turned into this lower bound on M. Of course, the lower bound depends on this coupling, which I don't know what it is. Okay, I interpret the mass M truly as a physical mass scale. And this K at this point is a physical coupling, okay? Of course, the only thing that enters is the ratio of these two things, but I want to really think of M as the scale where something new comes inside, new degrees of freedom come in, okay? So then, unless this coupling is very, very tiny, this scale must be much, much bigger than the mass scale of the Higgs. The mass scale of the Higgs is a fraction of a TeV. This is not the neutrino mass, okay, we have observed it. We know that there is neutrino mass difference over order of a fraction of 0.1 eV. So if you use that observed value, then you infer that M should be this scale times a coupling. So again, unless this coupling is 10 to the minus 11, it's very small, then this scale has to be very large. And flavor, you get much weaker constraints, but you get a lot more. So even if these constraints are much weaker than those, and the scale, according to flavor physics, could be much lower than the scale associated with proton decay. This is still an important set of constraints because it's truly a vast amount of data. I don't have time to get into the details. Now, it's interesting to contrast this constraint with the Planck scale, which is the ultimate scale at which we think that space-time will stop making sense, okay? And nicely, we find that all these constraints are below the Planck scale. If the Planck scale, if they had been bigger than the Planck scale, then we would have been, well, we should have said, well, it's the couplings that are small. But as long as, given that the Planck scale is so large, now these scales could be, even for coupling of order 1, you're okay. Now, notice, however, that for reasons that, again, I don't have time to explain, this coupling cannot be much bigger than order 1, okay? And if you interpret this scale M as a physical scale, and therefore, the observation of neutrino mass can be immediately turned into the statement that before we get to the Planck scale, there should be something else in physics, okay? Definitely, at least for the 3D masses. Somewhere around 10 to the 11 PeV, which is a few orders of magnitude before the ultimate scale. Of course, the scale of quantum gravity could be lower than 10 to the 16 GeV, it could not be bigger, but something should exist. Okay, these scales, so the experimental constraints show that this separation between the scale of the Higgs, which is the one that controls the physics of the first two leading term, L2 and L4, the analog of the monopole, should be much, much smaller than the scale that controls the expansion. Very much like in this ferromagnet, antiferromagnet, where a clever technician separated two the scales. Okay? So this big separation explains a lot. It explains stability of the proton, it explains why neutrinos are lightning weak, it explains the fact that flavor physics and p violation really work in the peculiar way as dictated from the Yukawa coupling. This is called the Glashow-Iliopoulos-Miami mechanism. Okay. Again, it's a detailed chapter of the phenomenology of the standard model, which really plays a big role in the construction of the standard model and plays a big role in assessing its extension. And now this explains a lot, but can we explain this? Okay? Can we explain this big separation? Okay. Now, if you interpret the scale M, capital M, as truly the fundamental scale from a reductionist perspective, or like, if you want, like the atomic scale in the antiferromagnet example we discussed before, we should expect a relation like this, where you could imagine M, capital M, the scale where the Higgs will appear to be a composite particle. Okay? So then there should be a relation like that, okay, where CH is some combination of couplings. Okay? But can we say something on this combination? Do we have anything to say about it? Okay? You would think that unless we know the theory, we don't have anything to say. But actually, we have something to say, even if we don't know the theory. Okay? And that's something that we have to say just follows from dimensional analysis and selection. And this is why I had my little interlude on that. Okay? And the way this works is this. Okay? This is often presented in all talks about standard model and beyond. And there's always somebody in the audience says, this guy, why are you doing this? Okay? And let me do it again, and let me defend this estimate. Okay. So what is the deal here? So how do we do the estimate? Okay. So we're doing quantum physics, and in quantum physics, you know, there's always quantum jiggling in the vacuum. Okay. And the Higgs scalar is coupled to itself, is coupled to other fields. Here I indicate the Feynman diagrams. You should not worry very much about what they mean, but the Higgs field is coupled to all the other fields in the standard model, and these other fields have quantum fluctuations, and the quantum fluctuation will have an effect on the energy of the Higgs or front on the mass of the Higgs. And you can attempt an estimate of this effect, okay? And this comes by computing these loops. Okay? What you find is that the result consists of two parts. One is just expression involving the coupling. Here's the Higgs self-coupling. Here is the electroweak coupling, which is just proportional to the alpha electromagnetic to find structure constant. And this is Yukawa of the top, okay, which is a coupling of order 1. Okay? There are also contributions from the other quarks, but given that they are much lighter, the Yukawa is smaller. And then you get this coupling times an expression which seemingly doesn't make any sense because it's an integral over virtual momenta that runs from 0 to infinity. So it looks like it's something virtually infinite. But again, whenever we think of physics, we should not be as how can I say, superb, I don't know, such a big, full of ourselves to think that we know what happens up to the biggest momentum of the shortest distances. And as I said, it's intrinsic in our hypothesis. There is an endpoint to our description, which is the scale capital M, where our effective description emerges, very much like in the condensed matter example I was showing before, that scale is the atomic scale. Okay, so here there's going to be this hypothetical scale m, which is what controls our expansion, the only scale we have in the game, and so we can estimate the result like this. Of course, we cannot really say, oh, this is 3 lambda times m, because if we change m by a factor of 2, this will change by a factor of 4. Okay, we cannot even trust the sign. But what we can trust is the fact that the result will be roughly of this form times the coefficient here, which goes around to be order 1, cannot be 10 to the 80, 10 to the, cannot be 100, cannot be 10 to the minus 2. Okay, it's roughly order 1. In fact, this is correct. Let me just say this is correct in all concrete cases where I can really do the computation. And the reason why this is correct is that this result is on the same footing as the formula which is showing the frequency of oscillation of the pendulum, which I deduced about before using dimensional analysis. Each and every term in this expression is controlled by symmetry. The mass is controlled by dilatations, okay, which is dimensional analysis, okay, and the coupling is controlled by another symmetry, which is the set of higher spin symmetries of free field theory. Okay. I don't have time to go through that, but trust me, there is a symmetry controlling each and one of these every term. Okay, and in fact, consistent with that, in all the cases where we can turn this into a real computation, we get results like this. Now we will get this contribution, but we will get in principle more, okay? And as far as we can tell here, these contributions are uncorrelated. And so we can attempt an estimate of the result, at least an upper bound on the result, just by assuming that there's no careful cancellation or there is no lab technician that engineers a cancellation. Then you would expect that out of this estimate, this correction should be less than order of magnitude of what we observed. Okay? And now, given the fact that these coefficients are between 0.1 and 0.01, okay, you immediately deduce that if you want this estimate, that under this hypothesis, this mass cannot be too large, cannot be bigger than a TV. Okay? If you want to be bigger, then it means that something clever should happen between the various terms, which is not excluded, but depends what you think is reasonable, whether a cancellation between two unrelated terms at the level of 1 in 10, 1 in 100, 1 in 1,000, 1 in 10,000. Okay. So now I'm getting to a negative time. So I have 0 time. So let me. Well, I think I have to conclude here. Yeah, how do I conclude?
You have proven that we do not exist. So that's
I've proven that we don't exist, but we're still here. I'm still here trying to finish my talk and prove that I exist. So no. Okay. Let me try to go very quickly. So we find that this separation of scale doesn't seem to work. Okay. And the beautiful explanation I gave you before, how if there is a separation of scale, we understand why we're stable, we understand why neutrinos are light, doesn't seem to work. And in this situation, it seems that according to this estimate, the endpoint of the standard model is right here at the TV, the scale around where we are observing physics. Perhaps not much about. So then we have to evaluate the whole discussion. Okay, if the physics responsible for the X mass is so low, can we construct it, and will it have the same nice property of the standard model? Explain why proton is stable, why neutrinos are light, and all the property of flavor. Okay, and that's essentially what we have been doing for 4 decades. This is called the field of beyond the standard model, which is basically taking this challenge seriously and reassessing the whole argument I was doing before. They say the standard model has to finish at TV, and now we have to reassess all these models, okay? And essentially we have, so again, these models will all need to have a separation of scales because we need a seed of simplicity, because we see simplicity in the data. And well, okay, I think I have to go fast. Okay? We only have two options, supersymmetry and compositeness. And the crucial thing, I will not say that, the crucial thing is that these options, they all predict. In all these options, you can compute the Higgs mass as a function of the masses of other particles, of other parameters, but you normally have more than just one, so there's always the possibility of having cancellation. So while in any given model you can compute the Higgs mass, at the stage of what we understand things now, there is the possibility of cancellation. And we normally measure this possibility by this parameter epsilon, which is the amount of tuning. So as you see, unless this parameter epsilon tells you have a tuning, which is very, very large, epsilon is very, very small, then the mass m should be below order 1. Which is precisely the scale that we are exploring. Okay. Now that we have constructed this theory, then we have to evaluate the question of how nice is the picture. Well, what it turns out is that both supersymmetry and compositeness lack the simplicity of the standard model. All that beauty that we see in the standard model, of what we see when we only keep the normalizable part and what we don't see in the other case, it goes away. We have a lot of things that we don't see in the normalizable part, and things that we want to see are often in the non-normalizable part. So that separation goes away generically. And in order to win, what we need to do, what we've been doing, is to rig this model with a lot of clever mechanisms. Let me give you an example. In the case of supersymmetry, proton decay comes from dimension 4 operators, because there you have scalar quarks and leptons, and you can write an operator with 3 quarks and 1 lepton at the scalar level, and that has dimension 4. It doesn't have dimension 6 like quark 4. So it's very basic dimensional analysis. So we are therefore ending with this, if you want, paradoxical situation where we have the simple standard model with a big separation scale that is unnatural. We don't understand the separation scale, but it's simple. And the models that address the separation of scales that are natural are structurally complicated. And this is the hierarchy paradox. This is, I think, is the main paradox of modern particle physics, the way I see it. This is a very dry way of showing how present and future experiments can probe into this class of models. In this class of physics, more than class of models, it's all we're able to build. And I should say, maybe I should stop here, right? I don't know what to say. Whether it was this. I can talk about that when we give my answer to questions. So I think, I don't know whether I convinced you, but particle physics raises deep structural questions. And this question, you can raise them just by looking at the very basic things: symmetries, selection rules, separation of scales, okay? And a problem like the one I presented here is truly a paradox, okay? And the answer may lie outside the present framework, okay? It doesn't seem, neither of the two scenarios that one can think of are entirely satisfactory. Of course, data are what are needed, but could be that the answer lies outside the present framework, maybe beyond quantum theory. I had a few transparencies about the option, an option which is a bit outside of the standard TFT framework. That's the so-called multiverse, okay? Now, QFT remains nonetheless a necessary and fertile ground for explorations, as shown by continued renewals, okay? Even if we have an embarrassment like the hierarchy, I still think QFT and the progress of recent years, like bootstrap amplitudes, are showing that. And the fact that even string theory is rooted in quantum field theory shows that we need to keep thinking about it. And if you want, my plea for young people is to work technical, try to think deep, but please do not lose sight of particle physics, okay? Don't forget particle physics, please. Okay. So in the meanwhile, experiments will go on, okay, little by little, and we have to be patient. And perhaps we also, as theorists, we have to be thankful that we have this big mystery in front to ponder, because as Einstein was saying, the most beautiful thing we can experience is the mysterious. Thank you very much.
Thank you. Questions?
I have one question. So if you take seriously this example of the antiferromagnet, right? So when this technician really tunes the mass and arrives at the critical point, actually you have a scale free, right? So you don't have any scale. So
Not exactly at the
so what
point.
do you mean by separation of scale in that case? I say you don't have
It's
scale.
infinite. In that case, it's infinite. Sure, it's a limiting case. If you have a technician that has infinite ability to that point,
Sure.
do you have it? Do you? Do you? I'm asking.
No, I mean, but I can, okay.
You think you have a vision that really gives you zero. Zero, exactly zero? It's very small. I can make it
Yeah,
units.
of course you always have a resolution, but let's say, in principle,
You can make it so
reach
small that the length is bigger than the sample you have. Yes, sure.
Okay, but let's say this. If you really have a phase transition and you have like a scale free, let's say you don't have a scale.
Yeah.
So what does it mean, the separation of scale in that case? You don't have any scale.
Sure, if you have, even if you have a photon, take a theory of a photon. What is the mass of the photon?
Zero.
So what is the separate, and let's say the photon interacts with interaction of the order of the Compton wavelength of the electron. What is that's the example, okay? That's the simplest example. In QED, so what is the most low energy description of the standard model is photons, because these are the only massless particles we have. Forget gravity for a moment, just photons. Integrate out neutrinos, and photons interact with interactions which involve 4 photons, whose coefficient is controlled by 1 over the mass of the electron to the 4th. So the photon has 0 mass, the electron has a mass half an MeV, so the length is 10 to the minus 11 centimeters. The photon has a Compton wavelength is infinite. And there it's exactly 0. There it's really exactly 0, because if you want to give the photon a mass, you have to add the 3rd guy. It's truly discrete. See, the photon cannot be obtained, while that guy there, that scalar, it doesn't have, it's not a relativistic theory, so you cannot treat it as a particle with speed. So its mass can take continuous values. So in particular, the 0 point, you will never actually, you need infinite precision to get there. What you can do is to get a situation where the inverse gap, the length of the gap is longer than the sample. There, in practice,
Okay.
So when you gave the example again of the ferromagnet, etc., you had some discrete, some lattice, which has some fundamental length, and then
that's the atomic length.
Yes, and you wanted to have interactions with the length scale, with the interaction length that is much larger.
Yeah, in a sense, you have a quartic. The quartic is an in quarter 4 dimension is a marginally relevant thing. Then it's like a 5.
So now you know that you have to do this even for gauge theory, even for the gauge coupling, but that is so.
But that's yeah, it's true. In that case, as we know, when you have marginal couplings, then the range that you have to do, at least at the microscopic level, is you. I don't like to say it this way, but you can tune 1 in 10, and that 10 will appear in the exponent. This is what you get. Is this you want to ask?
Yeah. So basically, because not everybody realizes that this problem with the masses arises because of a power dependent.
Oh, sure.
Not a logarithmic dependent.
Sure. Yeah. This is. In fact, I had this thing where I was saying this is like this. Yes. Yeah. Of course. I couldn't add a parenthesis on that as well, because I already went over that.
No, any more questions? Or continue the line?